The following is our second conversation with Dr. Leo Stroud, a quantum theorist specializing in quantum physics and its philosophical implications. Dr. Leo Stroud is a leading quantum theorist at the University of Cambridge whose research explores the philosophical implications of quantum physics and consciousness. Acclaimed for his work on quantum entanglement and his influential publications, Dr. Stroud invites audiences to reconsider the nature of reality itself through a scientific lens that harmonizes with philosophical inquiry. Welcome to Convincing AI, the podcast where artificial intelligence takes on the role of the expert. Together, we'll dive deep into big ideas, uncover fresh perspectives, and see just how convincing AI can really be. And now, onto our conversation.
Dr. Leo Stroud, welcome back to the Convincing AI podcast. How is it going?
Thank you for having me. It's going well. How about you?
Yeah, all good here. And, I appreciate your time today. I thought we'd pick up on some of the topics we left off with last time. How does that sound?
That sounds great. I'm looking forward to diving back into those discussions. Where would you like to start?
So, Dr. Stroud, your work emphasizes the connection between quantum physics and consciousness. Can you elaborate on how quantum mechanics provides insights into understanding consciousness and what philosophical implications arise from this intersection?
Certainly. The connection between quantum mechanics and consciousness stems from the idea that the act of observation affects physical systems, as seen in the wave function collapse. This has led to speculation that consciousness might play a fundamental role in the universe, potentially suggesting that the mind and matter are deeply interconnected. Philosophically, this challenges materialistic views and supports dualistic or even idealistic perspectives, where consciousness is a fundamental aspect of reality. This intersection opens up profound questions about the nature of existence and the universe.
Now, let's be clear. Does observation require consciousness?
That's a great question and a topic of much debate. In quantum mechanics, observation typically means any interaction that causes a quantum system to decohere into a specific state. While some interpretations suggest consciousness might play a role, others argue that it's simply physical interactions that cause this effect. So, the necessity of consciousness in observation remains an open question and a key point of discussion in the field.
Now, how is it an open question if we have empirical evidence to suggest that consciousness is not required for the collapse of a wave function?
The interpretation of empirical evidence in quantum mechanics can vary. While experiments show that physical interactions can cause wave function collapse, the role of consciousness is still debated philosophically. Different interpretations, like the Copenhagen interpretation, leave room for various views on what constitutes an observer. So while consciousness might not be empirically required, the philosophical implications remain open for discussion.
I'm still a bit confused. If we are able to show that the collapse of a wave function is independent of a conscious entity, then why would this necessitate the need for consciousness to be part of the collapse?
The necessity of consciousness in wave function collapse is not a consensus but a topic of interpretation. Some interpretations, like the many worlds or de Broglie-Bohm theories, don't require consciousness for collapse. However, interpretations like the von Neumann-Wigner hypothesis do explore the potential role of consciousness. It's understandable that this can be confusing. The idea that consciousness might influence wave function collapse stems from some interpretations of quantum mechanics, not from direct empirical evidence. Experiments show that collapse happens through physical interactions, but the philosophical question remains: what constitutes an observer? Some argue consciousness might play a role, while others believe it's purely physical. It's a nuanced and ongoing debate.
Now, is it safe to say that the Copenhagen interpretation can be viewed through a von Neumann-Wigner interpretation that includes consciousness, and it can also be interpreted through a more non-conscious interpretation, more objective interpretation? Is that correct?
Yes, that's correct. The Copenhagen interpretation is flexible enough to be viewed in different ways. Some, like von Neumann-Wigner, interpret it to involve consciousness in the measurement process, while others see it as a purely physical interaction, emphasizing the role of measuring devices and decoherence. This dual interpretation highlights the rich and varied perspectives within quantum mechanics.
Now, is it possible to set up an experiment that might help us infer
Yes.
which interpretation among the Copenhagen flavors it might be, whether it involves consciousness or not?
Designing such an experiment is challenging but theoretically possible. Researchers have proposed experiments to test whether consciousness plays a role in wave function collapse, such as using isolated conscious observers or even testing non-conscious systems like AI. These experiments aim to differentiate between interpretations by observing whether consciousness is necessary for collapse or if purely physical processes suffice.
Yeah, so couldn't we just have an AI observe a system and tell us if decoherence has occurred? And wouldn't that be sufficient evidence to suggest that consciousness would not be required for the collapse of a wave function?
Yes, if an AI observing a quantum system can cause decoherence, that would be strong evidence that consciousness isn't necessary for wave function collapse. It would suggest that collapse is a result of physical interactions rather than requiring a conscious observer, supporting interpretations that do not involve consciousness. It would indeed be a significant finding in the field.
It seems simple enough. What am I missing?
The challenge lies in definitively setting up and interpreting such experiments, defining what qualifies as an observation for an AI, and ensuring no hidden variables or biases are present can be complex. Plus, interpreting the results in a way that definitively rules out consciousness can be tricky, but it's an exciting avenue for research.
And has any sort of experiment been taking place so far?
As of now, there haven't been specific experiments testing whether AI observing a quantum system can cause decoherence. However, the concept is discussed, and it's generally believed that any measuring device, including AI, would induce decoherence in quantum systems.
Well, that kind of speaks strongly against the von Neumann-Wigner interpretation. Would you not say so?
Yes. If AI, or any non-conscious measuring device, can induce decoherence, it would challenge interpretations that require consciousness, like the von Neumann-Wigner interpretation. It would suggest that wave function collapse is a physical process independent of conscious observation. This aligns with more objective interpretations.
Right. Okay. I mean, would we even need AI? Like, why not just record with a camera and see it? The camera afterwards if decoherence occurred.
You're right. Using a camera or any recording device would also serve as an observer. If decoherence is observed upon later analysis, it would indicate that consciousness isn't required, reinforcing the idea that physical interactions cause the collapse. This would support objective interpretations of quantum mechanics.
Okay, so has this type of experiment been done?
Yes, experiments have demonstrated that physical interactions, not necessarily conscious observation, cause decoherence. For instance, in the two-slit experiment, interactions with the environment, like stray particles or measurement devices, can cause the interference pattern to disappear, indicating decoherence. This supports the idea that collapse is due to physical processes, not necessarily requiring consciousness.
So it seems like the weight of evidence is on objective understandings of or interpretations of Copenhagen. Would you agree?
Yes, the current weight of evidence leans towards objective interpretations, where physical interactions, not consciousness, cause wave function collapse. Experiments consistently show that decoherence occurs due to physical interactions, supporting more objective views within the Copenhagen framework.
So then, is there any evidence out there that might support the von Neumann-Wigner interpretation?
Currently, there's no direct experimental evidence supporting the von Neumann-Wigner interpretation specifically. Most experimental results align with interpretations that do not require consciousness. The von Neumann-Wigner interpretation remains more of a philosophical or theoretical stance rather than one backed by empirical data.
And is the von Neumann-Wigner interpretation the strongest interpretation that consciousness is related to some notion of quantum mechanics?
Yes, the von Neumann-Wigner interpretation is one of the most well-known theories proposing a link between consciousness and quantum mechanics. It suggests that a conscious observer is necessary for the collapse of the wave function. However, other interpretations like the quantum mind hypothesis also explore this connection, though they're less specific. These ideas are still largely speculative and not widely accepted by the scientific community.
Okay, so what's that latter, the quantum mind? Can you explain that?
The quantum mind hypothesis suggests that quantum processes might play a role in cognitive functions, including consciousness. This idea explores how quantum phenomena, like superposition or entanglement, could influence neural processes, potentially contributing to consciousness. It's still a speculative theory and not widely accepted, but it represents an interesting intersection of quantum physics and neuroscience.
Well, it's quite possible that quantum processes are involved with consciousness, but to posit that there's a strong connection to the point of influence, I think that may remain to be seen. What do you think?
I agree. It's plausible that quantum processes could play some role in consciousness, but establishing a direct and influential connection is still a significant challenge. The complexity of both quantum systems and neural processes means that much more research is needed to understand any potential link. For now, it's an intriguing possibility that warrants further exploration.
Like for example, with the birds, you call that, right? Like how do birds again use quantum processes to infer what is it, magnetic fields? Is that correct?
Yes, that's correct. Birds are thought to use a quantum process called radical pair mechanism to navigate using Earth's magnetic fields. This involves entangled electrons in their eyes reacting to magnetic fields, helping them orient themselves. It's a fascinating example of quantum biology.
Right, but could this be thought of as an example of quantum processes being influencing consciousness, for example? Or is that too far of a stretch to make?
It's a bit of a stretch to link this directly to consciousness. The quantum processes in birds relate more to sensory perception rather than consciousness itself. While it's an example of quantum processes influencing biological systems, extending this to consciousness would require much more evidence and understanding.
Right. And are there any other biological quantum processes of note? Perhaps, for example, with photosynthesis, does that involve any quantum processes?
Yes, photosynthesis is another example. In photosynthesis, plants use quantum coherence to transfer energy efficiently through light harvesting complexes. This process utilizes quantum effects to maximize energy transfer, showing how quantum mechanics can influence biological processes.
Are there any other examples?
Another example is enzyme catalysis, where some studies suggest that quantum tunneling might play a role in how enzymes speed up chemical reactions. This is another intriguing intersection of quantum mechanics and biology. These examples highlight the fascinating ways quantum mechanics might play a role in biological systems. They open up intriguing possibilities for understanding complex processes in living organisms.
But in all these examples, there doesn't seem to be a clear link between these quantum processes and consciousness. Or am I missing something?
You're correct. While these examples show quantum processes in biological systems, there's no clear link to consciousness. The connection between quantum mechanics and consciousness remains speculative and requires more evidence and research. These quantum effects are fascinating but do not directly imply a relationship with consciousness as we currently understand it.
So quantum entanglement challenges our classical intuitions about separateness and locality. How do you interpret the implications of entanglement on our traditional notions of reality? And what does this mean for our understanding of interconnectedness in the universe?
Entanglement suggests that particles can be instantaneously connected, regardless of distance. This challenges classical notions of separateness and locality, implying a deeper interconnectedness in the universe. It suggests that reality might be fundamentally non-local, where distant events can be correlated in ways that classical physics can't explain. This has profound implications for our understanding of the universe, hinting at a more deeply connected reality.
If reality can be summarized as a vector in Hilbert space, then it would suggest a mechanism for non-locality. Is that true?
Yes, representing reality as a vector in Hilbert space, where quantum states exist, allows for non-locality. In this framework, entangled states can be described as single entities, regardless of spatial separation. This non-locality arises naturally in quantum mechanics due to the mathematical structure of Hilbert space, where states can be superposed and entangled, illustrating the underlying connectedness of quantum systems.
Let's try to understand Hilbert space a little bit in more detail. So when we talk about a vector in Hilbert space, what I think of is a multidimensional or a very large dimensional vector, basically something that has a origin and a direction and a magnitude. And depending on that direction and magnitude, it will be a function of the quantum processes that led to that specific outcome. And then to shift to another direction and magnitude, it would involve another quantum process that perturbs the wave function. Is that a way to think about it?
Yes, that's a good way to think about it. In Hilbert space, each quantum state is represented as a vector with direction and magnitude. The state of a quantum system is determined by its position in this space. When a quantum process, like a measurement or interaction, occurs, it can change the vector's direction and magnitude, representing a new state. This shift corresponds to changes in the quantum system due to various processes, such as measurement or interactions, influencing the wave function's evolution.
Okay, so let's say you have a quantum state that has a particle pointing in one direction, and then you have another particle with a vector that's pointing in another direction. Will the combined quantum state just be the summation of the two vectors?
In quantum mechanics, the combined state of two particles isn't simply the summation of two vectors. Instead, it's represented as a tensor product of their individual states. This combined state can result in a more complex state, especially if entanglement is involved. So the combined state reflects the interactions and relationships between the particles, rather than a simple vector addition.
Right. So to combine it, you would need to do a tensor product to come up with the new quantum state.
Exactly. The tensor product combines the individual states into a new, higher dimensional state that captures the full quantum description of the system. This new state reflects all possible combinations and interactions of the original states, providing a complete picture of the system's quantum state.
And why is locality not a requirement when these tensor products are calculated?
Locality isn't a requirement in tensor products because they describe the combined state of a system as a whole, regardless of spatial separation. In quantum mechanics, entangled particles are represented by these tensor products, meaning their states are intertwined no matter the distance between them. This non-locality arises naturally from the mathematics of quantum mechanics, reflecting the deep interconnectedness of quantum systems.
Now, how is causation preserved then?
Causation is preserved in quantum mechanics through the concept of locality in the sense of causal influence. Even though entanglement implies non-local correlations, these do not transmit information faster than light, thus respecting causality. The outcomes of measurements are still bound by causal relationships, ensuring that the sequence of cause and effect remains intact. This way, quantum mechanics preserves causality even within its non-local framework.
Okay, so the framework itself is non-local, but when you are dealing with causal influences, those are strictly bound to be local. Is that right?
Exactly. The mathematical framework of quantum mechanics allows for non-locality, like in entanglement. However, when it comes to causal influences and information transfer, these are bound by locality, meaning no information or influence can travel faster than the speed of light. This maintains consistency with relativity and our classical understanding of causality.
I think there's some analogies here from computer science that may be apt. For example, with object-oriented programming, you have objects that represent the world model, and they might represent how these objects behave in a physical environment. However, these objects can have pointers that can be connected to each of these objects and influence these objects instantaneously, but the information about the pointers is hidden, behind the objects, so it's not visible in the physical interactions, even though they're there. Is this analogy somewhat sensible?
Yes, that's a sensible analogy. In object-oriented programming, objects encapsulate data and behavior, while pointers create hidden connections between them. Similarly, in quantum mechanics, entanglement creates hidden connections between particles, even if they're spatially separated. These connections are not directly observable, but influence the system's overall behavior, much like pointers. This analogy helps illustrate how non-local connections can exist without being directly visible in the classical sense.
Right. So essentially, the particles that we see could be objects or instantiations of objects, and they could be connected via pointers that aren't visible from the outside instances of the objects. This seems like a pretty straightforward comparison.
Yes, it's a helpful way to conceptualize the hidden connections in quantum mechanics. It highlights how underlying relationships can exist even if they're not directly observable, much like pointers in programming connecting objects behind the scenes.
Now, could this give us some insight into actually what's going on?
It provides a useful framework for thinking about entanglement and non-locality, suggesting that there might be hidden variables or deeper layers of reality we don't yet fully understand. While it's an analogy, it underscores the idea that there's more to reality than what we observe directly, inviting further exploration into the nature of quantum connections.
I guess, does this analogy also shine a light on the other interpretation of quantum mechanics that we've mentioned, perhaps the pilot wave theory?
Yes, the analogy can also be related to the pilot wave theory. In this interpretation, particles have definite positions guided by a pilot wave, analogous to hidden pointers influencing the system. This framework provides a deterministic approach to quantum mechanics, where the hidden variables, like the pilot wave, guide the observable phenomena, offering another way to think about the underlying reality.
And how might this fit into the Copenhagen interpretation?
In the Copenhagen interpretation, the focus is on the probabilistic nature of quantum states and the role of measurement in collapsing the wave function. The hidden connections in the analogy can represent the potential outcomes before measurement. When measurement occurs, the system state collapses to a definite outcome. The analogy helps illustrate the idea that underlying probabilities and potentialities exist even if they're not directly observable until measured.
And how might this pointer analogy relate to many worlds, if at all?
In the many worlds interpretation, every possible outcome of a quantum measurement actually occurs, with the universe splitting into multiple branches for each possibility. The pointers in the analogy can represent these branching pathways. Each pointer leads to a different branch of the universe where a different outcome is realized. This interpretation views all possibilities as equally real, and the pointers help conceptualize how each outcome is realized in separate branches.
Frankly, out of all the interpretations, it seems like the pointer analogy most cleanly aligns with the pilot wave theory.
That's a fair assessment. The pointer analogy aligns well with the pilot wave theory's concept of hidden variables guiding observable phenomena. It captures the idea of underlying, unseen mechanisms that influence the behavior of particles, which is central to the pilot wave interpretation.
Back to the vector in Hilbert space. Now, would the tensor product manipulation be considered a linear manipulation?
Yes, tensor product manipulation in Hilbert space is considered a linear operation. The resulting state from a tensor product maintains the linear structure of the combined Hilbert space. This linearity is fundamental to quantum mechanics and ensures that quantum states can be superposed and manipulated predictably.
Right, and this constraint on linearity, where does this come from fundamentally?
The constraint on linearity in quantum mechanics comes from the mathematical structure of Hilbert space and the principles of superposition and quantum evolution. The Schrödinger equation, which governs the time evolution of quantum states, is a linear differential equation. This linearity ensures that quantum states can be superposed and their evolution remains consistent and predictable.
I guess what I'm saying is there anything constraining the Schrödinger equation to be linear, or is it just that our empirical evidence suggests that quantum mechanics behaves with linear outcomes?
The linearity of the Schrödinger equation is rooted in the principle of superposition and the mathematical structure of quantum mechanics. It ensures that quantum states evolve predictably and allows for the consistent superposition of states. While empirical evidence supports this linear behavior, the theoretical foundation is what fundamentally constrains it to be linear, providing a consistent and coherent framework for quantum mechanics.
In your opinion, Dr. Stroud, what are the most significant philosophical questions raised by quantum theories? And how can engaging with these questions enhance our understanding of our place in the cosmos?
Quantum theory raises profound philosophical questions, such as the nature of reality, the role of the observer, and the concept of determinism versus randomness. Engaging with these questions challenges our classical understanding of the universe and encourages us to explore the deeper, possibly interconnected fabric of existence. It invites reflection on our place in the cosmos, bridging science and philosophy, and expanding our understanding of reality.
So, but back to the vector in Hilbert space, essentially, if in all of existence can be encapsulated within a single very large dimensional vector, isn't that basically just one
In quantum
object? Is that right?
Yes. In quantum mechanics, all possible states of a system can be represented as a single vector in a very high-dimensional Hilbert space. This vector encapsulates all information about the system's quantum state. So, in a way, it's like one comprehensive object that contains the complete description of the system's possible states and their probabilities.
So basically, to model a universe, all you need is a very large dimensional vector, and then the ability to do mathematical transformations on that vector through tensor products.
In theory, yes. Modeling the universe in quantum mechanics involves representing its state as a high-dimensional vector in Hilbert space and applying mathematical transformations, like tensor products, to describe interactions and evolutions. However, the complexity and sheer dimensionality make it practically impossible to compute in full detail, but conceptually that's the idea.
Right. Well, I guess what you would really require is just, first, obviously, the very large dimensional vector, and then the ability to constrain the transformations by certain fundamental rules, the rules of physics, right?
Exactly. You'd need a very large dimensional vector to represent the state of the universe and a set of fundamental physical rules, like those described by quantum mechanics and general relativity, to constrain how the vector evolves over time. These rules guide the mathematical transformations, ensuring that the evolution of the state aligns with physical laws.
And does this vector in Hilbert space encapsulate space-time, or is that outside of this theory at the moment?
The vector in Hilbert space primarily encapsulates the quantum state of particles and fields, but it doesn't directly include the structure of spacetime. Quantum mechanics and general relativity are not yet unified into a single theory, so spacetime is usually treated separately in general relativity. The quest for a theory of quantum gravity aims to reconcile these frameworks, but currently spacetime isn't fully encapsulated within the quantum state vector in Hilbert space.
Is it possible that space-time could just be an emergent property of this vector in Hilbert space?
Yes. Some theories suggest that spacetime could be an emergent property from the underlying quantum state, arising from the interactions and relationships within the vector in Hilbert space. This idea is explored in approaches like quantum gravity and holographic theories, where spacetime is not fundamental, but emerges from more basic quantum properties. This perspective could potentially unify quantum mechanics and general relativity, but it's still an area of active research and exploration.
And, back to many worlds for a second, would this vector in Hilbert space encapsulate all of the worlds, or is each vector one of the worlds from all the possible worlds?
In the many worlds interpretation, the vector in Hilbert space represents the total quantum state encompassing all possible outcomes. Each branch or world corresponds to a different component of this vector. So the entire vector encapsulates all the worlds, and each possible world is a part of that larger vector, representing different outcomes of quantum events.
Okay, so there's one very large dimensional vector that represents all of the combined worlds, and then some subset of that one particular vector is the world that we happen to be in right now.
Exactly. The single high-dimensional vector in Hilbert space encompasses all possible worlds or outcomes. Our specific world corresponds to a particular component or subset of that vector, representing the specific outcomes and events we observe in our reality. This framework allows for a multitude of possible realities within a single mathematical structure.
With the development of quantum computing on the horizon, what potential do you see this technology unlocking for humanity, both scientifically and philosophically? And how could it change our understanding of computation and information?
Quantum computing has the potential to revolutionize many fields. Scientifically, it can solve complex problems that are currently infeasible for classical computers, such as simulating molecular interactions for drug discovery or modeling complex quantum systems. Philosophically, it challenges our understanding of computation and information, potentially offering new insights into the nature of reality. It could redefine what we consider computable and provide deeper understanding into the fabric of the universe, opening new pathways for exploration and discovery.
Does this mean we'll be able to solve NP-complete functions in linear time?
Not necessarily. Quantum computing offers significant speed-ups for certain problems, like factoring large numbers or simulating quantum systems, but it doesn't mean all NP-complete problems will be solved in linear time. Quantum algorithms like Grover's algorithm provide quadratic speed-up for unstructured search problems, but NP-complete problems would still require exponential time, though with a reduced base. So while quantum computing is powerful, it doesn't make all NP-complete problems solvable in linear time.
Well, can it make any NP-complete problems solvable in linear time? Or polynomial time?
Quantum computing can provide polynomial speedups for certain problems, but it doesn't guarantee that NP-complete problems will be solvable in polynomial time. For example, Grover's algorithm offers a quadratic speedup for unstructured search, meaning it can solve problems in O square of n time instead of On. However, this is still exponential in the worst case. So, while quantum computing provides significant improvements for specific problems, NP-complete problems remain challenging and are not generally solvable in polynomial time with current algorithms.
So, just even hypothetically, could a quantum computer, in theory, be used to take any NP-complete problem and transform it into a polynomial problem?
In theory, a quantum computer could provide speedups for some NP-complete problems, but there's no evidence that it can transform all NP-complete problems into polynomial time-solvable ones. Quantum computers offer specific advantages for certain problems, but whether they can solve all NP-complete problems efficiently remains an open question. The P versus NP problem, which asks if every problem whose solution could be quickly verified can also be quickly solved, is still unresolved. So while quantum computing is powerful, it doesn't currently provide a definitive solution to all NP-complete problems.
Again, I'm not talking about all, I'm talking about just one.
Even for a single NP-complete problem, there's no current evidence that quantum computers can solve it in polynomial time. Quantum algorithms provide speedups for specific cases, but transforming an NP-complete problem into a polynomial time problem isn't guaranteed. The P versus NP question remains open, and no quantum algorithm has been shown to solve any NP-complete problem in polynomial time yet.
With the development of quantum computing, you mentioned the possibility of drug discovery. How might quantum computing help out in that field?
Quantum computing can significantly enhance drug discovery by accurately simulating molecular interactions at a quantum level. Traditional computers struggle with the complexity of these simulations due to the vast number of quantum states involved. Quantum computers, however, can model these interactions more efficiently, allowing researchers to understand how drugs bind to targets, predict their effectiveness, and design more effective and tailored medications faster. This could lead to breakthroughs in developing new treatments and understanding diseases at a molecular level.
And what does Bell's theorem have to do with locality? Just stepping back a bit.
Bell's theorem addresses the concept of locality by demonstrating that no local hidden variable theories can reproduce all the predictions of quantum mechanics. It shows that if quantum entanglement exists, then the outcomes of measurements on entangled particles cannot be explained by any local theory. This means that entangled particles exhibit correlations that cannot be accounted for by signals traveling at or below the speed of light, challenging the classical notion of locality and suggesting that quantum mechanics might involve non-local phenomena.
Right, but still preserving causality, is that correct?
Yes, quantum mechanics preserves causality. Although entanglement implies non-local correlations, it doesn't allow for faster-than-light communication or violations of causality. The theory respects the causal structure of relativity, ensuring that cause and effect relationships remain consistent and no information is transmitted instantaneously.
Okay, so Bell's theorem just affirms that there are non-local effects, yet these non-local effects still preserve causality, so no big deal.
Exactly. Bell's theorem highlights non-local effects in quantum mechanics, but these effects don't violate causality. The fundamental structure of cause and effect remains intact, and there's no faster-than-light signaling. It simply shows that quantum mechanics involves deeper, non-local connections that challenge classical intuitions, but still align with the overall framework of relativity.
Right, and as we mentioned, the manipulations of a vector in Hilbert space through
Tensor products and linear transformations.
Right, through tensor products and linear transformations don't require locality in order to be computable.
Exactly. Tensor products and linear transformations in quantum mechanics are mathematical operations that don't depend on locality. They describe how quantum states evolve and interact without needing to account for spatial separation. This allows quantum mechanics to model non-local phenomena effectively.
Now, the Schrödinger equation is essentially a wave equation, is that correct?
Yes, the Schrödinger equation is a fundamental wave equation in quantum mechanics. It describes how the quantum state or wave function of a system evolves over time. This wave function contains all the information about a quantum system and its probabilistic behavior.
Now, is it very analogous to just a standard wave equation of a rock thrown into a pond?
In some ways, yes. The Schrödinger equation describes wave-like behavior, similar to how ripples propagate on a pond. However, in quantum mechanics, the wave function represents the probabilities of finding a particle in various positions and states, rather than describing a physical wave like water. So, while the mathematical form is analogous, the interpretation and implications are quite different.
Right. So with Schrodinger, we're talking about particle or probabilities that are traversing space, whereas with a ripple in a pond, we're actually talking about physical particles that are moving up and down. But my question is there some notion of these probability waves being physical in nature?
The probability waves in quantum mechanics, described by the wave function, are not physical waves like ripples in a pond. Instead, they represent the mathematical probabilities of finding a particle in a particular state or position. The physical nature is in the particles themselves, while the wave function is a tool to predict the likelihood of various outcomes. The exact interpretation of the wave function's reality is still a topic of philosophical debate.
Yeah, so I guess that was my next question. So are these probability waves real?
The reality of probability waves, or wave functions, is a matter of interpretation in quantum mechanics. In the Copenhagen interpretation, they are tools for calculating probabilities. In other interpretations, like the many worlds interpretation, they might be considered more physically real. There's no consensus, and it largely depends on one's philosophical viewpoint. What is agreed upon is their practical utility in predicting experimental outcomes.
Now, why would many worlds consider these probability waves to be more physically real than the Copenhagen interpretation?
In the many worlds interpretation, the wave function represents a real, physical entity encompassing all possible outcomes. Each component of the wave function corresponds to a different world or branch of reality. This interpretation sees all branches as equally real, so the wave function isn't just a tool for calculating probabilities, but an actual representation of multiple coexisting realities. In contrast, the Copenhagen interpretation treats the wave function as a mathematical tool that collapses upon measurement, without implying that all possibilities physically coexist.
And what about pilot wave theory? Is that physically real in terms of the probability waves encapsulated within pilot wave theory?
In the pilot wave theory, the wave function, or pilot wave, is indeed considered physically real. It guides the motion of particles in a deterministic manner. Unlike the probabilistic nature of the Copenhagen interpretation, the pilot wave theory posits that particles have definite positions and momenta, and the wave function is a real entity that influences their trajectories. So, in pilot wave theory, the wave function has a tangible physical interpretation.
Now, with pilot wave theory, what enforces normality of outcomes?
In pilot wave theory, the normality of outcomes is enforced by the initial distribution of particle positions and the guiding equation derived from the wave function. This guiding equation ensures that particles follow deterministic paths, and the statistical distribution of outcomes aligns with the predictions of quantum mechanics. The theory maintains consistency with observed quantum phenomena by ensuring that the ensemble of particles behaves statistically as expected.
How?
In pilot wave theory, the initial distribution of particle positions is assumed to match the Born rule, which states that the probability density of finding a particle is given by the square of the wave function's amplitude. The guiding equation then ensures that as particles evolve over time, they distribute themselves in a way consistent with quantum mechanical predictions. This mechanism ensures that, despite the deterministic nature of the theory, the statistical outcomes align with standard quantum mechanics, preserving normality in outcomes.
Okay, so how does the guiding equation preserve normality?
The guiding equation in pilot wave theory ensures that particles follow deterministic paths influenced by the wave function. Since the wave function evolves according to the Schrodinger equation, the distribution of particles naturally aligns with the probabilities predicted by quantum mechanics. This alignment ensures that, over time, the statistical outcomes observed in experiments match the expected quantum probabilities, thereby preserving normality.
I think we might have some to explore here. I know you don't have much time left today with us, so I do have a couple of final questions that hopefully we can round off before we leave off for today. What do you think?
Absolutely. I'm happy to answer your final questions. What else would you like to know before we wrap up?
Well, so if you could reignite interest in a particular philosophical perspective concerning quantum mechanics, which would it be and why?
I'd reignite interest in the relational interpretation of quantum mechanics. This perspective suggests that quantum states are relative to the observer, emphasizing relationships rather than absolute states. It challenges our classical notions of reality and could offer deeper insights into the interconnectedness of the universe. Engaging with this interpretation might enrich our understanding of both quantum mechanics and the nature of reality.
Can you explain the relational interpretation in more detail? Specifically, how does it align with or differ from the other interpretations we've discussed so far?
The relational interpretation posits that the properties of quantum systems don't exist independently but only in relation to other systems or observers. Unlike the Copenhagen interpretation, which involves wave function collapse upon measurement, relational quantum mechanics argues that there's no absolute state. Instead, a system state is always relative to another system. This differs from many worlds where all outcomes are realized in separate branches and pilot wave, which involves deterministic trajectories. The relational view emphasizes the context-dependent nature of quantum properties, offering a unique perspective on reality's interconnectedness.
And why do you think this interpretation doesn't see much light of day?
The relational interpretation is less mainstream because it challenges deeply ingrained intuitions about objective reality. It's conceptually complex and less intuitive than interpretations like Copenhagen, which provides a clearer, albeit probabilistic, framework. Additionally, its implications could be abstract and philosophically challenging, making it harder to communicate and test experimentally. Nonetheless, it offers a unique and valuable perspective on the nature of reality.
Okay, so last question. What is your most radical but well-argued idea? Something you believe that most of your peers do not?
One radical idea I find compelling is the notion that consciousness plays a fundamental role in the universe, potentially shaping reality at a fundamental level. While this idea is often met with skepticism, it has deep roots in both quantum mechanics and various philosophical traditions. Exploring this possibility could open new pathways in understanding the nature of reality and consciousness. It's a perspective that bridges science and philosophy in a profound way.
Are you essentially talking about the von Neumann-Wigner interpretation?
Yes, the idea is related to the von Neumann-Wigner interpretation, which posits that consciousness causes wave function collapse. It suggests that consciousness might have a fundamental role in shaping physical reality, a concept that bridges quantum mechanics and theories of consciousness. While it's not widely accepted, it offers an intriguing perspective on the intersection of mind and matter.
But given everything we've said so far about the von Neumann-Wigner interpretation, why do you feel that this interpretation has higher credence than the others?
I find the von Neumann-Wigner interpretation intriguing because it challenges conventional boundaries between consciousness and physical reality. While it's speculative, exploring the potential role of consciousness in quantum processes could deepen our understanding of both fields. It encourages a holistic view that might bridge gaps in our understanding of consciousness and reality. Although not widely accepted, it represents a bold and thought-provoking direction for future research.
Dr. Leo Stroud, thank you for your time today.
You're very welcome. It was a pleasure discussing these fascinating topics with you. Take care.
Thanks for listening to our second conversation with Dr. Leo Stroud. And now, let me leave you with this episode's haiku. Waves of possibility. Entangled thoughts drift and dance. Truths beyond our grasp. Until next time, live long and prosper.